Hello and welcome. I have had this idea in mind for the last few weeks, and finally last Sunday I decided to give it a try. I have to say it's pretty simple actually, but the end result can be very satisfying. So let's take a look at the basic idea. So inside Houdini, let's create a geometry node and a sphere with radius 3. Is offset with 100 divisions, so we can now scatter points inside the sphere. Okay. For my final rendering I've used 250 points here, but let's start with 50. Okay. So now, if you are familiar with constraints in RBD or Vellum simulations, you should already know the node connect adjacent pieces, but this time we will use it to create our network. Just select the adjacent points option, increase the radius, and max search points set to 6. So we now have at most 6 connections for each point. And this is our network. Obviously, if we increase the number of points, we have a more dense network. But this is the basic idea. So now create another sphere. Maybe a little less. Okay. And just copy 2 points. And we have a sphere for each intersection. Okay. So now we are going to work on this side of the branch. We can use a facet to split each segment with the option unique points, and a resample node to create other points along the segments. Even more, because we are going to apply some noise to it. Okay, and in the resample node, activate the curve view attribute. So we now have a curve view. For each segment, we have a curve view going from 0 to 1. And for the noise, we want to keep the intersection points where they are, because they represent the position of the spheres. So we can create another attribute based on the curve view. Let's call it distortion chramp based on the curve view. Smooth. Let me create a point in the middle, 0.5, and this one will be 0. Okay, now our distortion attribute should look like this. So we have the maximum distortion in the middle of the segments. And now we can use a point VOP to add some noise. So let me distortion attribute segment noise. So we are going to add a noise to the position attribute. Let's use the anti-alias noise, position, and let's grab the attribute distortion that we have just created, bind, multiply the noise by the distortion attribute. Okay, so we can now promote a few parameters. And we have our noise. Which doesn't touch the intersection points, so when we merge the spheres and the segments, okay. Now we can use a polywire let's decrease the radius a little bit and increase the divisions. Okay, and what I don't like here, I mean, I would like to see a more slim radius in the middle. So we can create another attribute after the distortion, put down another attribute triangle, and this time we can use the p-scale attribute, chramp p-scale based on the curve view. Smooth, and this time it will be 1 at the end, at the beginning and the end, and another point in the middle with a value of I don't know, let's start with 0.5. This is the p-scale attribute, and now we can tell polywire to use the p-scale. And now we have what we want. Just a little bit slim here in the middle, and we can always go back to the p-scale and scale it down. Okay. It's now time to switch to SDF. Let's create a VDB from Polygon. And let me set the voxel size to 0.01. Use a VDB smooth. Okay, and convert to polygon on the VDB, back to polygons. Maybe we can set a mountain for the spheres to have a more interesting result. Mountain. Amplitude okay, and we can play with the settings until we are satisfying, but we have our geometry. Let's now talk about the animation. If you watched my previous tutorials, you know exactly what I'm going to do now, because it's pretty much the same. So after the noise, we can create another wrangle. Let's call it energy attribute. So define a parameter t equals to time for now, and the energy will be equal to fit the curve view attribute between times minus 0.1 and time between 1 and 0. And let's set the energy attribute. And now we have something growing along the segments over time. Like this. Okay. And we can remap the energy, so energy ch ramp energy shape, it's something like this. Okay, now we have just a segment along. Okay, we can increase the length of the segment increasing this parameter here. Okay, but we now have just one cycle ending around the frame number 30, so we can use the modulo and now we should have multiple cycles. Okay, now everything is synchronized, so every segment has the same animation, the same speed. By the way, we can define a speed attribute here, chf speed, and multiply our time for the speed. So we have a global control over the speed. Speed 1 will be the same as before, but now we can slow down. Okay, and speed up. Fine. So let me create another parameter. Let me see. After the sample, if we visualize the prim numbers, we have a prim for each segment. So we can use a primitive wrangle. Okay, and let me define a seed. And now we can say float, let's call it local speed is equal to a random number based on the prim number plus the seed fit 0,1 between half the speed and twice the speed. Okay, and this is we are running over primitive, so we have to set this attribute over the points of the primitive. So int pts is equal to prim points 0 prim num, and for each int pt in pts set point attrib 0. The attribute is local speed. The point is pt and the value is local speed. Okay, local speed attribute. Now here we can use a local speed times f at local speed, and we should have different speeds for different segments. Okay. We can now transfer the attribute over our geometry with a attribute transfer. Energy. Okay. And smooth the, blur the attribute. Maybe 50 iterations. Let me see. Okay, seems fine. Now, obviously, it's a good idea to cache on disk the geometry. File cache. Not time dependent. Let's call it neural network. Save to disk. Okay. So we can use the energy attribute over the surface to drive the emission of the material. So let me go back here, create a camera. And let's go to material and create a material builder. Neurons. So we have our attribute energy, rs user data, scalar user data, energy. Let's create a color mix. Basically, I'm defining the emission color. So the first color is black, which is no emission at all. And the second one is blue, some blue. Okay. And the mix amount is our parameter energy. And we can use this one as emission color. Oops. Okay, for now, let's just apply the material. And let me open a redshift render view. Okay. So material. We have to activate the emission, obviously. Let's say 2 for now. And the material is well, no reflection for now, very little reflection. Transmission very high. Base color black. And now we start seeing something here interesting. Maybe let's try to increase the emission. Okay, so in my final rendering, I have used another color. Yeah, as you can see here is blue. The energy is blue, but when it reaches the spheres, it becomes yellow. So my idea is to create another attribute here after the oh, maybe even before the energy, it doesn't matter. Let me create some space here. Attribute wrangle. Let me call it e-color, emission color, chramp color based on f-core view. Smooth. E-color attribute. Let me visualize it. E-color. And this time is a point in the middle, 0.5. 0 beginning and end, and we can also add a couple of points here, 0.2 and 0.8. Okay, you see now we have basically I want blue here and yellow here, so we can transfer also this attribute here, e-color, and e-color. Just to give you an idea, I can change the visualizer. So we have remove, remove, and remove. The red one will be our blue, and this one will be our green. This is the idea. Okay, so let's go back to the material. Now we have a new attribute called e-color. And instead of using this one, the input 2, instead of using the blue, we can use a ramp, RS ramp, between a yellow and a blue. Input and input. Okay. And now you see that the sphere when the energy reaches the sphere, it becomes yellow. Okay. And basically that's it. Thanks for watching.